Alright, time for another draftphysics.com, debatephysics.com also. Video presentation. Yeah. Yeah. So this will be about the coincidences. And the fact is a lot of people keep bringing up this moment where they played the Luan experiment, okay, in the video. And I'm pointing out, well, yes, it's a free energy experiment. And I also tried to point out that later in the same exact lecture, Professor Luan essentially performs exactly the same experiment all over again, except it's a little different. All right, so there's no springs, okay, and it was supposed to be a Velcro stick experiment, and it turned into a no stick experiment, and they bounced. And clearly way short of the 185, okay, this number should be. It's clearly way short of even half the velocity. So less than half the velocity, that means less than half the energy, half the it's twice the mass, okay? So whoops, I lost the thing. So it's a one mass cart going into a two mass cart. Boom. And so it's the same experiment. It's just that, like I said, it didn't stick. And, in the previous experiment, we saw that 100 goes in, 133 leaves. That means it went faster than half the velocity. All right. And clearly here, if it was going to be half the velocity, it would have been 222. And it's way higher than that. It means it took longer than that. A lot longer than it should have taken. And clearly not consistent with the first example of the experiment. Now, yes, you can make excuses. Oh, the Velcro consumed a whole bunch of the energy. Well, you can watch the experiment and there's no sign of that. Gotta go more like here.
I've spent
that's
$7.7
disappointing.
million of my own money on YouTube ads.
Zoning.
Right, and he's done that $7.7 million of ads to make money. He needs money. He's got $7 million to burn, and he needs to make money. Oh, I see. Why do the people who are rich need to make commercials about how to get rich, and they have to get rich making the commercials on how to get rich? If they're already rich, why don't they just do it for free? Oh, yeah, good question. Anyway.
% off. That's completely within my prediction that each time could be off by 2.5%. Now I will have a car.
So you can see the number. This 138 means that was the speed going in. So obviously in this example, he's put in a little more velocity. All right, and this was one car becoming two cars and then leaving at twice, one half the velocity. So it's pretty much almost perfect, right? This would be almost a little bit short. This would be 276. So 276 to 288. So we know that almost all of the momentum was conserved, and in fact we lost one half the kinetic energy. So in this experiment where a 1 sticks to a 1, and now it's a 2 leaving, it's got a little tiny bit less than half the velocity. It's conserved 99% of the momentum, and yet it's lost half the kinetic energy. Somehow everything got really hot. A lot of heat went flying all over the place. That's your argument. That it's just a coincidence that nothing melted and there's no smoke. Yeah. Anyway, so right there, that experiment proves the point. You lost half the kinetic energy, yet you conserved almost 100% of the momentum. And that makes logical sense to you people calling me a fool. Amazing.
It's twice the mass. And this is once the mass.
And no clay on it. Okay. So no springs. All right. So it's going to be a real elastic collision in the sense that they're going to bounce honestly. No spring to create the backwards direction.
I will set them again to 0. And now we get one onto double the mass.
So they're supposed to stick. And
ready?
Okay, so when he has to let go of the cart right at the point, because the fact is the track isn't perfect and the carts move all by themselves, which is a real problem. It's a $10,000 air track and it still has these problems where the carts don't stay where you put them. Alright, this should be able to work. And so far, so bad.
There we go.
Should work. Okay, I think it's working. You just can't see it because nothing's moving. And there comes the cart. Okay, you can see this, right? So I just want to show this for the sake of anyone saying that, oh, it's stuck and the Velcro took some of the energy. It's not going to be any sign of the Velcro consuming any of the energy. No sign of it whatsoever. So it hits, bang, it's gone. No evidence that it's stuck at all. And clearly the one cart's following the other cart, so that's where the rest of the momentum is. The part that's missing, the part that's short of half the velocity. So the higher the number, the slower the cart, just to be clear. And there you go, the end. And it just clearly demonstrates that, oh, the experiment comes out different ways if you do it different ways. Yeah. But it's just a coincidence that this number isn't a little higher. So it's not nearly as high as it should be. I mean, lower in the sense of being more consistent with more momentum. There's supposed to be 133 in this case. So it went in with 100, let's say it's supposed to be 133. So it didn't gain anything. So there's no 33, and there's even less than that. There's less than 100. So it's leaving with 85. So 100 went in, 85 is going out. In the previous experiment, 100 went in and 133 went out. So it's way short of that. And it's just a coincidence, though. Don't pay any attention. Just a coincidence. Okay. All right. So the other coincidence experiment is the MythBusters. So there's just no doubt about what they did. They spent a lot of money and crashed 2 cars. Okay. Identical cars. Scooted them down the track. Okay. So it was done with the machine. It pulls the cars. And it lets go of them right at the right before they hit the wall. So same wall, same car. And what had happened? It's just a coincidence that the car going 100 miles an hour and a 50-mile-an-hour car. And it's just a coincidence that the 100-mile-an-hour car crushed exactly. Okay, the amount crushed. All right, is exactly twice the amount crushed, okay, in the other case. So exactly twice as much crushing, that is twice as much removal of car. All right, so and it's just a coincidence. It just happened to be that the car gets harder to crush at exactly the same amount as what would be required to produce that result, to make all the kinetic energy disappear. So, I mean, this car is supposed to have 4 times the impact, and it's only twice the damage. That's all there was. Twice the crushing of the car. And it's just a coincidence that the car becomes harder to crush at exactly the same rate that would be consistent with momentum being the correct answer. That all you have is momentum. All right, and then you have the ballistic pendulum example again. Okay, you shoot the bullet. I probably should have the bullet over here. Into the big, heavy ballistic pendulum. And you're trying as hard as you can to collect this energy, its momentum, its power in this direction. So it has a kinetic energy of, say, 2,000. You make up any number, doesn't really matter. And all you can collect is 2. A little less than 2. So all you collect is 1.8. So 2,000 goes in, only 1.8 comes out. Yet the momentum numbers are just fine. It had a momentum of, let's say, 2, and you got 1.8. So everything's just fine that way. You know, you expect that you're losing some because the bullet's going to move some clay in directions and it's going to heat some clay. And so it makes perfect sense that all of this direction won't be captured. So you're a little short of conserving the momentum, but you're way short of conserving the kinetic energy. And it's just a coincidence that this, you can't make this number even a 3 or a 4. You know, that you can't be short 97% of the kinetic energy lost instead of 99.94%. So instead of 99.94, you can't even get up to 97. It's just a coincidence that it stayed below this momentum number. Because yes, if you could get 97%, then you would have 3.6 in momentum, and you would have made free momentum. So you could show me the free momentum experiment again, right? But no, it didn't happen. It can't happen that way. So with all our technology, a MIT scientist, right, can't collect more than 0.06% of the kinetic energy. That's all an MIT scientist can collect of this energy that's supposed to be so important, this kinetic energy, this living force. Somehow an MIT scientist can't collect any more than 0.06%. 0.06%. That's all he can collect. 0.06%. And, you know, and I'm the fool, because I don't understand how all of these coincidences are perfectly reasonable. Yes, you can't crush cars because crushing cars isn't scientific, and it doesn't work because the car gets harder and harder to push, which there's no facts that say that's true, actually. It's actually harder to crush the first 30 miles an hour, and then it gets easy. You know, once you go to past a certain speed, all of the devices put into the car to create resistance to crushing start failing, and now you're just crushing. You know, it gets easy to crush because it's not designed to be hard to crush over those speeds. You know, the frame isn't specially engineered to be really powerful at the back end of the car. You know, there's nothing resisting the motion. Once you get the engine moving, you're going to be out of luck in terms of how much the car is going to crush. But no, it's just a coincidence. So it's a coincidence that his you know, that the experiment that failed, in the sense that he did the experiment a different way, and it didn't come out anything like the first version of the experiment. Completely the opposite, in the sense perfectly consistent with momentum being the rational theory and kinetic energy being a nonsense. And it's just a coincidence that it turned out exactly that way, exactly consistent with conservation of momentum, and no evidence of any bullshit about, oh, we lost energy this way, and that energy subtracts from this, we can cancel energy. Just a coincidence. Is that the argument? So I'm just saying, you know, again, if people are going to call me a fool, then draw one of these experiments and explain how you make it rational. That you can understand how all the kinetic energy just disappeared here somehow. It just went somewhere. Where'd it go? And why won't your physics show me where it went? You know, just put a thermometer on there and see where did all this energy go? You lost more than half of the kinetic energy in this case. Where'd it go? Where is it? Alright, that's probably enough. But it's just bullshit to say that they in any way showed the Professor Luan experiment and therefore demonstrated how it's a perfectly valid experiment, when the whole point of me addressing it was to show, look, they do these experiments, they perform this theater for their audience, But it's just that. It's theater for the audience. It isn't science. It isn't, we're really going to test it. It's, we're going to show it, not test it. And if they had done the test with a little more depth, okay, it wouldn't come out their way. Again, you could ask the question, why in every single case where they're doing an elastic collision, do they do a superelastic collision? That is, why do they always put springs when it should be metal against metal should work just fine? Ball bearings bounce off of anvils really well. Another example, by the way. So you really, let me just write that down. You know, if we're going to call people fools, I mean, you really fall for this shit. You're really so dupable that you'll actually believe this is actually going to happen. That I have a nice heat-treated anvil. I bounce a nice, you know, silicone, whatever, it doesn't matter. Well, it does matter, frankly. They found that the glass things bounce more than the steel things, but it's, you know. But for the sake of argument, somebody has got it to bounce 200 times. Now, obviously, okay, the bounce diminishes, and, you know, 70 of the bounces will be in this almost imperceptible range, and only 30 of the bounces are going to be good ones. But the fact is their theory is this ball drops, let's say, with a 100 momentum. That's how much you put in. It hits with 100 momentums, all right, and 200 momentums go into the anvil. And then it bounces almost all the way back, and so now I'm going to get 99. So that'll be a plus 198, okay, because this one's going to come back down again and hit. And then it's going to bounce all the way, almost all the way back up again. All right, now I'm going to get 82. And then I'm going to get 164. And then I'm going to get, these are all plus signs, plus sign, plus sign. So 100 in, and I'm going to make maybe 2,000 out. In terms of momentum I put into the anvil. And it's just a fact. If I suspend this anvil with 2 wires or some kind of way where it's absorbing the energy, okay, not something else absorbing it, I put it on even a, you know, some sort of device that crushes. Okay, so there's a crushable device between the anvil, like a hunk of clay, okay, and the earth. So now I can't move the earth. I'm just going to crush the clay. So with each bounce, I crush more clay. I keep crushing clay. I keep crushing clay. I keep crushing clay. 2,000 worth. 100 in, 2,000 out. You think that's rational physics. You think the physical universe can do that. You don't think that the fact that it bounces all the way back means this object didn't move. That I can't, I mean, look, they could do the experiment with a different weight. You know, instead of a 2 mass, use a 3 mass, then it's 150, then it's 50 free momentums. And if they make it a 5 mass, then it's 170. And they make it a 6 mass, then it's 180. So all I have to do is go up to a high enough mass where the thing barely moves, but moves. And as long as it moves, it means I put 100 in, I can get 199 out. Free momentum. That's their theory. That's what they say is the absolute truth. It absolutely happens in reality. And you're going to call me the fool. Because I say, bullshit, that happens. Bullshit, that's reality. No chance. Because it would be exploited. Because it's free energy. Free momentum is free energy. Damn. All right, so that's it. So counter arguments, please. But if you're going to make a counter argument, you're obviously going to have to draw the experiment and show us how it works differently than what I just said, and how what I just said isn't paradoxical nonsense. You can't make free momentum.